Hi. In the first section, we'll present a proof of Pythagoras' theorem using domino tiles, blending algebraic and geometric approaches. In the second section, we'll explore the connection between Pythagorean triples and consecutive sums through a 2D truncated pyramid, again utilizing domino tiles. This will ultimately lead to an alternative formula for Pythagorean triples, which will prove equivalent to the well-known formula. In his book, The Pythagorean Proposition, Elijah Loomis offers a thorough examination of 370 proofs of the Pythagorean theorem, organized into 4 categories: algebraic, geometric, quaternion, and dynamic proof. This diverse range of methods highlights the various approaches used to demonstrate this fundamental principle in geometry. Loomis first references an article by Dr. Artemas Martin in which he explains that a simple algebraic proof can be framed as a difference of squares. The square of x plus y minus the square of x minus y equals 4 times x times y, where a perfect square can be obtained only if x times y is itself a perfect square. By assuming x equals m times a squared and y equals m times b squared, where m is bigger or equal to 1, we can express the equation as the square of m times a squared plus m times b squared minus the square of m times a squared minus m times b squared, which is equal to the square of 2 times m times a times b. After factoring out the common factor m, we are left with the square of a squared plus b squared minus the square of a squared minus b squared, which is equal to the square of 2 times a times b. We can approach this proof with a geometric aid, using dominoes, the kind of insight that emerges while playing with your kids, making this proof potentially useful for teaching. A domino tile has a rectangular shape, allowing us to define its size as b for the base and h for the height. Now, we can construct a square by arranging 4 domino tiles, with 2 of them rotated 90 degrees. Once placed, they form a larger square with sides of length h plus b, while also creating an inner square with sides of length h minus b. To prove that the difference between the areas of these squares is itself a square, we compute the square of h times b minus the square of h minus b, which equals 4 times h times b. Since 4 is a perfect square, it follows that h times b must also be a perfect square. Now, we impose that the restriction that h and b are integers, though the argument will ultimately hold for real numbers as well. For h times b to be a perfect square, either both h and b are squares, or they share a non-square common factor m. So we can summarize this as h equals m times the square of lowercase h, and b equals m times the square of lowercase b, where m, h, and b are bigger or equal to 1. We can visualize this in the figure. Since the area of the larger square is m squared times the square of h squared plus b squared, the area of the smaller square is m squared times the square of h squared minus b squared, and each of the 4 domino tiles has an area of m squared b squared h squared, we can combine these elements and rearrange to derive a general solution, like the one mentioned by Dr. Artemas Martin in Loomis' book. It's interesting to consider what happens when instead of an inner square positioned at the center, we have one placed in one corner. This arrangement leaves us with only 2 repositioned domino tiles, where we can now draw a large green square with sides h and a smaller purple square with sides b. The total area of the figure is given by the square of h times b equals h squared plus b squared plus 2 times h times b. That is, the sum of the areas of the green and purple squares plus twice the area of a single domino tile. If we focus on the purple square, then the combined area of the green square and the domino tiles must also form a perfect square. W squared equals h times the sum of h and 2 times b. Since we are working with integers, there are 2 possible cases. Either h is even or h is odd. In case 1, h is even. So h equals 2 times h sub 1. That is, w squared equals 4 times h sub 1 times h sub 1 plus b. So h sub 1 times h sub 1 plus b must be a perfect square. We set h sub 1 equals m times v squared and h sub 1 plus b equals m times u squared. Combining this, we obtain b equals m times the difference of u squared and v squared. Since the total area of the figure is given by the square of h plus b, we need just a few steps to reach the general solution. In case 2, h is odd, so the square of w equals h sub 1 times h sub 1 plus 2 times b. So h sub 1 times h sub 1 plus 2 times b must be a perfect square. We set h sub 1 equals m times v squared and h sub 1 plus 2 times b equals m times u squared. Replacing the first into the second, we obtain b equals half times b times u squared minus v squared. Now we get back to the total area of the figure and proceed with a few steps to reach the general solution. In conclusion, by combining algebraic and geometric approaches, we demonstrate how the formula for Pythagorean triples can be proved using domino tiles. This can be done by arranging two pairs of tiles at a 90-degree angle, or using just two tiles at the same angle while projecting lines to form two squares within the larger square. For primitive Pythagorean triples, a, b, and c, the numbers are co-prime, so 2 must be odd. If 2 were even, all 3 would share a common factor greater than 1, contradicting their primitiveness. Thus, we can safely analyze the difference of two odd squares and determine the conditions for it to be a perfect square. For this expression to be a perfect square, m plus n plus 1 times m minus n must also be a perfect square. If these two factors shared a common divisor, it would also appear in the sum to m plus 1 and their difference to n plus 1. But since we already assume they are coprimes, these factors must be coprime as well. Thus, we set m plus n plus 1 equals a squared and m minus n equals b squared. So the sum yields 2m plus 1, which equals a squared plus b squared, and their difference 2n plus 1, which equals a squared minus b squared. This leads to the fundamental formula for primitive Pythagorean triples. Now we connect primitive Pythagorean triples to consecutive sum of integers. Notably, the odd squares we are working with have a simple relationship with triangular numbers. Plus, the sum of the first m consecutive integers form a triangular number. This allows us to reinterpret the formula for primitive Pythagorean triples as 8 times the difference of two triangular numbers. We have already shown that m plus n plus 1 and m minus n must be coprime to form a primitive Pythagorean triple. Thus, each of them must be a perfect square. This highlights the equivalence of our approach. The fact that the difference of two odd squares is equivalent to 8 times the difference of two triangular numbers, which must be an even square to satisfy the conditions for a primitive Pythagorean triple. What's really interesting is that we can interpret the formula for primitive Pythagorean triples as a partition of a consecutive sum of integers into two parts. To illustrate this, let's consider an example using a 2D truncated pyramid. A domino tile typically has a height twice its base, making it a useful building block for constructing a truncated pyramid. In a truncated pyramid, we have 4 equal orange sides, a gray square at the top, and a single 1x1 white square. We can color the sides of the pyramid to facilitate the computation of areas, using the sides of the domino as the reference. This way, we identify 5 distinct areas, 4 identical ones, and a single white square at the top. For this specific case, we got that the area of the square at the top equals 7 squared, while the total area of the truncated pyramid equals 25 squared. and the area of the color sides equals 24 squared. Thus, we can construct a primitive Pythagorean triple by partitioning a consecutive sum of integers into two parts, multiplying each by 8 and adding 1 to both sides of the equation. Furthermore, we can determine where a consecutive sum of integers starts and ends. We first determine m using the square root formula, which allows us to pinpoint where the longer consecutive sum of integers begins and ends. Similarly, we determine n by applying the same approach to the shorter consecutive sum. Thus, the truncated consecutive sum formed by subtracting the short sum from the longer one begins at m and ends at n plus 1. Additionally, we can determine the number of elements in each partition, m, n, and m minus n. Note in particular that m minus n is a perfect square. In fact, when this truncated consecutive sum contains a square number of elements, it serves as a necessary condition for forming a primitive Pythagorean triple, as we will soon demonstrate. We can illustrate this with the example we have been working on. Not every combination of m and n works. A primitive Pythagorean triple can be partitioned into two consecutive sum of integers only when m minus n times m plus n plus 1 is a perfect square. In the given example, we can see that m equals 12, n equals 3, m minus n equals 3 squared, and m plus n plus 1 equals 4 squared. When m equals n times n plus 1 plus the square of 2k times k plus 1 all over the square of 2k plus 1, a generalization discovered through extensive examples, we obtain a perfect square for some integer k. However, additional divisibility criteria must also be met to obtain primitive Pythagorean triples. For integer solutions, 2k plus 1 must divide both 2k squared minus n minus 1 and 2k squared plus n. However, if it divides one, it must also divide the other, since the sum simplifies to 2k plus 1 times 2k minus 1. Furthermore, if 2k plus 1 divides both, then it also divides the difference, which equals 2n plus 1. Thus, the divisibility check simplifies. We first verify whether 2k plus 1 divides 2n plus 1, and if so, we check whether it can also divide 2k squared plus n or 2k squared minus n minus 1. These additional divisibility conditions may make the formula appear more complex, but in practice, generating Pythagorean triples remains fairly straightforward. Note the differences among the various values of n, which align with the value of 2k plus 1. We will explore these relationships further, but first, let's recap what we have established so far. Summing up, we can pull everything together and come up with an alternative, though a bit messier, formula for primitive Pythagorean triples, when 2k plus 1 divides 2k squared plus n and 2k squared minus n minus 1. With some algebraic manipulation, we can see that the square on the left side of the equation ultimately becomes a sum of two squares divided by a perfect square. And since the difference of the squares that are in the square on the left side of the equation equals 2n plus 1 times the square of 2k plus 1, then we can express the new solution in familiar terms, where a equals 2k times k plus 1 plus n plus 1, and b equals 2k times k plus 1 minus n. Let's get back to the table we've seen before, remembering that the differences among the various values of n align with the value of 2k plus 1. That can be stated as n sub u equals k plus u times 2k plus 1 for different values of integer u. Then, the condition that 2k plus 1 divides 2n plus 1 is easily matched, as that yields 2u plus 1. Given that the values of n sub u that satisfy the conditions for a specific k follow the pattern n sub u equals k plus u times 2k plus 1, we can substitute this expression into the formula for m sub u and then simplify the result. Thus, we arrive at a simplified alternative formula for Pythagorean triples. We will soon demonstrate that this alternative formula applies to all types of Pythagorean triples, not just the primitive ones, and that we can derive a specific formula for primitive triples by using k and u as variables, since we have already derived that. Replacing n for n sub u equal k plus u times 2k plus 1 and simplifying yields. Factoring out the common term, the square of 2k plus 1, we obtain a sub 1 equals k plus u plus 1 and b sub 1 equals k minus u. For this to generate primitive Pythagorean triples, one must be odd and the other even, ensuring that the sum or difference is always odd. This leads us to the equivalent expression where k and u are indeed integers. In conclusion, by constructing a truncated 2D pyramid using domino tiles, we illustrated how the formula for primitive Pythagorean triples can be understood as a partition of a consecutive sum of integers into two parts. Furthermore, we determined where such a sum begins and ends, as well as the numbers of elements in each partition m and n. However, not every combination of m and n works. A primitive Pythagorean triple can only be partitioned into two consecutive sum of integers only when m minus n times m plus n plus 1 is a perfect square. This condition holds when m equals n times n plus 1 plus the square of 2k times k plus 1 over the square of 2k plus 1 for some integer k. Though additional divisibility criteria must also be met, in practice generating Pythagorean triples remains fairly straightforward. We then derived an alternative formula for primitive Pythagorean triples in terms of n and k. While not particularly elegant, it can be rewritten through algebraic manipulation in the familiar form: the square of a squared plus b squared equals the square of a squared minus b squared plus the square of 2 times a times b, where a equals 2k times k plus 1 plus n plus 1 and b equals 2k times k plus 1 minus n. Since the values of n sub u that satisfy the conditions for a specific k follow the pattern n sub u equals k plus u times 2k plus 1, we substitute this expression into the formula for m sub u, simplify, and obtain this noble formula. Additionally, by factoring out the common term, the square of 2k plus 1, we can express the familiar form formula slightly differently. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. Consider subscribing to my channel for more elementary number theory content. Your support means a lot.